Hey guys, so today we are going to be doing a quick overview of indicators, and right now we're going to be first going through a paper slide of some parts of a 2010 Form B FRQ Problem 5. So first of all, let's just make a curve here that it's like nearly vertical. Actually, it is basically vertical, and that's just because this is where the equivalence point is. So let's just take a look at how indicators work when we look at this. First of all, indicator is basically a weak acid that acts as a natural dye and it changes colors as the pH changes. So what we're looking at here is going to be acid-base titration, where you have, like we look at in part A, you have an acid initially and you gradually add in NaOH as a titrant until you get the equivalence point where the moles of base equal the moles of acid and it's neutral. And the whole point of this titration is figuring out, well, number one, we want to get the S-shaped curve, and once you get the S-shaped curve, we can figure out where the equivalence point is, which is halfway between the vertical lines, right? So for part B, it actually wants us to circle the point that corresponds to the equivalence point, and we can see that it has a couple points out. 0, 10, 20, 30, 40, and halfway up still at 40, probably a little bit more, say like, and right here's about 50, and right here's about 60 roughly. Well, like I said earlier, you want to figure out where the vertical part is, which is going to be between 10 and 4 roughly. And then once you figure out the vertical part, you want to take halfway, so 10 plus 4, and then we want to divide it by 2 because you want a half, right? So that's going to be about 7. So the equivalence point is about 7, which is about right here, and we'll just circle that. Easy peasy, lemon squeezy. Okay, so next we're going to go to part C. Part C, it wants us to figure out how many moles of titrant have been added. So that's going to be a relatively simple calculation. The main thing we want to keep in mind is it's asking us for moles of titrant. So the in units is going to be moles, right? And what's a titrant? Well, we figure out initially in there it's going to be HCl, right? So the titrant has to be NaOH. Very simple, just logic. Okay, so let's just figure out what it gives us. It gives us 0.1 molar NaOH, right? Well, in that case, we can rewrite this as moles per liter because that's what molar is, right? So we can rewrite this as moles per liter. So that's going to be point. And we can see here we have 3 sig figs. Throw in that 0 in front just so you can easily recognize that there is a 0 in front. So it's going to be 0.100 moles of NaOH, and we're going to assume that since it's 0.01 moles, to get 0.01 molars, we're going to assume it's 1 liter, right? Okay, well, we want moles, but we have less liter right here, so we have to multiply something by liter, and this is just basic stoichiometry. We're going to look at the problem. It says a 40 milliliter sample of one of the solutions is added to a beaker to get equivalence point. And jumping back a little bit, we can see that, hey, wait a second, the equivalence point happens around 40, right? So 40 milliliters, well, that's going to end up being 0.04 liters, right? And that's a specific figure, so we can just keep the same number of sig figs, so 0.0400 liters. And then liters cancel, and we get 0.00400 moles of NaOH. Easy peasy. This is a measurement, and this is a measurement. Just keep your sig figs. Simple as that. And then for the last part, we're going to do part D, which is asking us to perform the same titration, but use an indicator this time. So I talked about indicators briefly earlier when we were doing part B, because I wanted to talk about it in relation to equivalence point. Now expanding on this a little bit, why would you use an indicator over just having a pH meter? Well, one, because I said earlier, right, like indicators are like dyes and they change colors. Having an indicator in there, you can get a rough sense of, hey, where is the equivalence point without having a pH meter. So it's useful if you don't have a pH meter. But on the other hand, if you have if you're doing titration, you kind of want to have the indicator in there, just to figure out, hey, about where you are, right? And keep in mind that we're going to be, in this case, it's asking us to do 1 for 3 indicators: methyl violet, methyl red, or alizarin yellow. There's something called universal indicators, and that's usually a combination of many different indicators. So it works from 1 through 14, but usual indicators work for smaller ranges. And that's where you get the thing between equivalence point and endpoint, because the equivalence point for titration is where the moles of acid equals the moles of base. But the endpoint of a titration may differ depending on how sensitive your indicator is. Okay, so without further ado, let's just go ahead and figure out the best indicator. So the main thing when you're figuring out indicator is taking a look at the ranges. So we have methyl violet, which is from 0 to 1.6, and this is your pH range. And then you have methyl red, which is from 4 to 6, and then you have alizarin yellow, which is from 10 to 12. Okay, well, let's just jump back to B again and take a look at the graph. Well, what do you want? Basically, you want to figure out where the endpoint is, and like we said, that's 7. That's why we circle this point. So we're going to just write here, since the equivalence point is at 7, approximately 7, and we're going to put beside it as this is from 4 to 10. Now we want to select an indicator with that range. Is closest to that range, and in this case it's going to be a methyl red, because 10 through 12 is obviously bigger than 4 to 10, and 0 to 1.6 isn't in the range at all, right? So we know it has to be methyl red, and you just write this. Okay, add in methyl red, and then just write this, and then easy peasy, you can solve a problem. Okay, so obviously the whole problem's on you, right? Substandard quality, unfortunately, we couldn't get the picture crystal clear, but you can, I'll pop a link below, and you can feel free to access it yourself while you're watching video. And now we're heading over and doing an actual indicator test. What do you mean if you see a phenolphthalein here, and then the methyl red with hydrochloric acid and the sodium hydroxide. So first of all, we'll be putting in some phenolphthalein indicator in a beaker, and this beaker is just distilled water with nothing else in it. And we're going to just put in a couple drops of phenolphthalein. Usually a drop or 2 is enough, but go and put in a little extra just for that zing. And you want to stir real well, which is like what you always want to do while you're doing titration. So we're going to put in the acid now. And one thing about phenolphthalein is that it turns purple really quick, but only after it gets past 7. So we're going to just keep on adding. And you can see when I pour it in that it turns purple. That's because temporarily the concentration of the area is bigger than 7. So it'll become nice and purple. You're going to just keep on adding a little bit. Now the thing is, I'm using. Okay, and here we go. Nice and purple and sensitive. Now, just as a quick demonstration, we're going to put in some hydrochloric acid. And in titration, you can see this better. But we're just putting in some hydrochloric acid to demonstrate that just how sensitive this indicator is. Maybe I went like a little overzealous on my base. Okay, there you go. So like you can see, it's really sensitive. Okay, so we're going to add some of this metal red in. And if you can see the little dots when it goes in. Now the way that phenolphthalein works, going back a minute, is that it changes color around the pH of 7, and like you saw earlier, it's totally sensitive, and it's like a single color change. It goes from clear to color, just like that. On the other hand, like we see in the picture right now, there's actually a range of colors for metal red, and on the right we actually have acidic solution, while on the left we went for basic solution to showcase the difference in colors. This is why on the right you see that pinkish reddish hue, while on the left there is a yellowish hue, and obviously the depth of a color represents how acidic or how basic an acid is. And like you can see right now, there's a clear contrast between the colors.